Alrighty, so in this video, we're going to go briefly over Newton's third law and then apply that into pushing a series of connected objects. Now, this isn't going to be like the connected masses lesson when things are connected by a rope. Instead, what these questions often look like is you're pushing a series of boxes that are touching. How much force does one box apply on another? Or how much do I apply on all boxes or whatever? And so as you can see on my picture, I have three different scenarios set up. With different, or actually they all have the same applied force, they all have different masses, and in all three scenarios, friction will be 5 newtons on all of them, just to keep it easy for today. So what Newton's third law says is that if I put a force on some object, that object will put the exact same force back on me. So if I got a desk right here, if I push down right now, I'm pushing down with, I don't know, 50 newtons of force. The desk is pushing back up on my hands with 50 newtons of force. If it pushed back on my hands with less force, my hand would sink through the desk. And if it pushed back with more force, my hands would go flying away. It would be really weird if the desk could shove my hands off. If the desk was to move, like if my pushing the desk was to actually lower the desk, there would still be equivalent forces, because if the desk was moving, I'm not pushing quite as hard, but it's not resisting as hard, right? So whatever force I apply on some object, it will apply the same force on me. The only time it wouldn't be the case is if my hand was to like break through the surface and it couldn't apply the same force on me, or if like a piece of paper, for example, if there's, or like a karate board, if you karate chop the board would apply the same amount of force in your hand, but when your hand caused it to break, it wasn't able to apply the same amount of force back on your hand, for example. But for all physics 20 questions, you apply force on something, it applies the same force back on you. So question 1 here, I'm going to apply a 50 Newton force on this box to this direction. Well, if and actually for the sake of this, I know we draw free body diagrams coming kind of from the middle, going out in the direction that the force is going, but I'm going to draw it like this. I am pushing 50 newtons on this side of the box. And then we could say, well, how hard does the box push back on my hand? Well, this one hopefully should be fairly easy. Well, if I'm pushing this hard on the box will push the exact same back on me. So it is actually going to apply a 50 Newton force back on my hand. Okay. What we can do now is look at the second example, and of course, calculating forces, inside of the box systems gets trickier. So far, so good. If I was to apply a 50 Newton force on this box right here, and I'm sliding these boxes across the floor, well, the point of contact between my hand and the box here is also going to apply the exact same 50 newtons back on my hand. If it didn't, if it was less, my hand would literally be breaking through the box, and now my hand would be located like inside because it could not supply the same force back in my hand, which again doesn't happen, or it could happen, but for physics questions it doesn't happen. So the box supplies the same amount of force back on my hand. Where the questions get tricky is where they will ask, well, what's the force that the 5 kilogram box is applying on the 10? Or the times when it really feels Newton's third law like is when they'll say, well, what's the force the 10 kilogram box is pushing back on the 5 kilogram box? Well, in order to figure that out, if we knew how hard the 5 kilogram box is pushing on the 10, well, it's the exact same number, because what one object pushes on another, that object pushes still back on the first. And so what we have here is this now proceeds similarly to a connected mass question when we learned about Newton's second law. And so we can look at the whole system, or we can look at individual boxes. So normally the way questions proceed is we look at the whole entire system first. And so we say, okay, I'm going to apply a 50 Newton force, and I'm going to put it here now, because we're looking at the whole system. 50 newtons is applied to the right, and that 5 Newton force is acting to the left. And so we want to say, okay, if I was ever to figure out how hard box 5 has to push on box 10, that would essentially be asking, what is the net force on box 10, or on the 10 kilogram box? Currently, we don't know the net force that the 10 kilogram box is experiencing. This 50 Newton force applied and this 5 Newton force of friction are the forces on the entire system, not the 10 kilogram, right? Because if you're pushing with 50 newtons of force, yes, that force has to move this 10 kilogram box, but it's also moving a 5 kilogram box at the same time. It has to move both. So you could think of it like you have to push harder to move both, but the amount of force that gets transferred to the 10 kilogram is not going to be the entire force you're using, because you're not moving just the 10 kilograms. So if I just made a dramatic example, a whole bunch of boxes are linked together. Think of them, they're each 1 kilogram, so they're really light. If you push on this side with 100 newtons, well, each one of these is so light, it doesn't take 100 newtons to push one box. But holy smokes, you add them up, it adds up weight. Now you need to apply a big force. Well, if the force being applied from this last box, second last box, and the last box, that's only pushing a little tiny box. So it doesn't need a huge force trying to push this front box. But this box has to apply a big force here because it's pushing all of this. So I'm going to go back to my example now. Okay, clear up some of this junk. Okay, so we proceed in a similar way to connected mass questions, where we look at the whole system first, and then we can divvy up and look at individual locations in between boxes, like we had done on like finding tension on a connected mass. And so we can say, all right, well, the first thing we always had to do was calculate acceleration, because we know these objects are going to move together, and as we can tell, we have an imbalance of forces. There's greater forces to the right, therefore these objects will accelerate. And when they accelerate, we know that there's a force applied, an F net. So F net equals force applied minus force of friction, which of course equals 50 minus 5, and so F net equals 45 newtons. And we know that that equals mass times acceleration. And so we are pushing this entire system of boxes. We are pushing a total of 15 kilograms of mass, right? We don't just put in the 5 because we are literally pushing on the 5 kilogram box, but we're moving 15 kilograms of stuff. And so, of course, we divide both sides by 15, and it turns out that acceleration equals 3 meters per second squared. That means both objects will accelerate at that rate together. One won't accelerate quicker than another. And so we have how quickly, essentially, our objects are going to speed up. So then what we do is say, okay, well, that was for the whole system. I want to know, how hard is box 5 pushing on box 10? 5 kilogram box pushing on the 10 kilogram box. And we say, okay, well, hold on. I know that this 10 kilogram box is going to be accelerating at 3 meters per second squared. So what net force on this box is required in order to, on this 10 kilogram box, to accelerate it at 3 meters per second squared? And it turns out the force that the 5 kilogram box must apply on the 10 kilogram box equals 30 newtons. If it applied less than 30 newtons on the 10 kilogram box, its acceleration would be less than 3, but we know from our previous calculation the acceleration has to be 3. And so we ask, how hard does it have to push this 10 kilogram box? The questions normally would have asked you instead, how hard does the 10 kilogram box push back on the 5 kilogram box? Well, we just figured out how hard the 5 has to push on the 10. Therefore, the 10 on the 5 is the exact same force. It's just in the opposite direction, negative 30 newtons. So first we looked at the whole system. Then we said, okay, now that I have acceleration, I know how quickly any of these boxes need to move. When I pushed, I'm pushing 15 kilograms of stuff. I need a bigger net force to accelerate it all. When this 5 pushed on the 10, it says, well, I'm only accelerating 10 kilograms of stuff at the same rate, but I'm pushing less material, therefore, I don't need to apply as much of a force. And hopefully you can kind of get into how that might affect our question 3 here. Again, 50 Newton force to the right, 5 Newton friction to the left. And so if I am pushing from this side, I am literally moving 3 objects. I'm moving 30 kilograms of material. So whatever force I am applying, it has to be big in relative to how much each of these boxes might apply on each other, because I'm moving a whole bunch of weight. The force in between these two boxes, the 10 kilogram box pushing the 15, well, whatever acceleration all of these boxes have, the force pushing the 15 kilogram object has to be less than the force I'm applying, because it's only moving a 15 kilogram object. I'm literally moving 30 kilograms, so I better be pushing harder. And so we go in the same way. We start with an F net equation equals, and we're going to add up all of the masses because I'm pushing, or sorry, before we do that, our F net, first of all, is equal to 50 newtons minus 5 newtons of friction. So again, F net, like before, equals 45 newtons. We know that this equals mass times acceleration, but since we're looking at the whole system, we're moving a whole lot of mass, we need to add them all together. And so that equals 30, divide by A. Oops, sorry, that's not what I meant. I meant divide by 30. And it turns out that A equals 1.5 meters per second squared. Excellent. So that is the acceleration of the whole system here. So no matter which box we're going to look at, we're going to find that each box accelerates at the same rate. Therefore, the forces will vary. So the force that the 5 kilogram box pushes on the 10, well, we say, okay, how hard does it have to push? It's moving 25 kilograms of stuff. Well, remember, I was moving 30 kilograms of stuff, so I had to push harder. It's only pushing 25 kilograms of stuff now. And so we can say, well, what's the force experienced from the 5 on the 10? And this has to do with, well, what's the mass it's moving? It's moving at 10 plus a 15, so 25, and it's accelerating at 1.5. Therefore, the force it's experiencing equals, I probably could do this in my head, but 25 times 1.5 is 37.5 newtons of a net force. Remember, my force applied was 50. The net force on the whole system was 45. But since I'm not looking at the whole system anymore, I now have a different F net. We're pushing a different amount of mass. So the 5 kilogram object pushes on the 10 with 37.5 newtons, or box 10 pushes back, Newton's third law, back on the 5 kilogram box with 37.5 newtons. And then we could do the exact same thing for the last question, which would be, what is the force that the 15 kilogram box pushes back on the 10 kilogram object? Well, okay, well, the 10 kilogram object is the thing pushing the 15. Whatever force it's applying on the 15 is going to be the same force the 15 pushes back on it. Well, let's figure out the net force. We know that we are moving 15 kilograms of mass, and we know that we're accelerating it at 1.5 meters per second squared. And so that means our total F net is going to equal, what's that, 22.5 newtons of force. So essentially, since all boxes accelerate at the same rate, that 1.5, there's a different amount of force needed to accelerate less mass. And so now the surface here is only pushing a lighter 15 kilogram object. Therefore, we expect a smaller force. Remember, the net force at the beginning applied on the whole system was 45. Then the F net at this surface was 37.5, I think. And now the F net at this surface is even less. So it turns out the further you go along, the less force required because we're moving less mass. And so the question I had asked was, what's the force the 15 puts back on the 10? Well, we just calculated the force the 10 puts on the 15. And so the force from the 15 back on the 10 is going to equal, well, it's the other direction, negative 22.5 newtons. Okay, hope you found this useful. If you have any other questions after this, definitely let me know.